All right, so today's lecture was about electric forces and fields. It starts off in chapter 20 of the textbook College Physics by Knight, somebody in Field. Can't remember all their names. Oh well. So let's get started. Before we actually go into the chapter, there's a few things we have to talk about. The first is what a system is and what an object is. These are ideas that carry throughout the course and throughout physics, and are something you really need a good foundation in. First off, we have systems. So a system is a defined part of the universe we've chosen to study. The universe is giant. It's got a lot of pieces. And to study physics, it would be overwhelming to take all of them into consideration. Instead, anytime we study something, we choose a specific system. We take a slice of the universe, define what we want that slice to be, and we look at it. Now, every system that we could choose has certain properties. The system would have charge, or it would have mass, or energy, or momentum. It'll have all of these things as some value. And it may have internal structure in and of itself. So, for example, you could get a Newton's cradle. Newton's cradle is the little balls that swing on the strings and whack into each other. And that is a tiny part of a giant universe, but we can look at the physics of that thing alone as a system. And that system would have a certain amount of mass, certain amount of charge, which is probably neutral because most things are neutral, certain amount of energy, depending on how much the balls are swinging, a certain amount of momentum, etc. And that system would have structure in and of itself. It would have a certain number of balls. It would have a certain tension of strings. And that structure would be inside the system. Now, on the flip side of that, we also have objects. Now, an object is a part of the universe whose structure we have chosen to ignore. And the reason we do this is as follows. Take the same Newton's cradle example. Every ball in a Newton's cradle has a bunch of atoms in it, like, I don't know, times 10 to the whatever, lots of atoms. And it would be crippling to have to consider every single atom and its movement when trying to describe the movement of the balls in a Newton's cradle. The atoms at that point aren't important. So what we do is we simplify. Instead of looking at the atoms, we look at, on a macroscopic level, the spheres swinging back and forth. So we choose to take each sphere as an object and ignore any structure that is inside of it. Our second important idea after systems and objects is that of conservation. Now, conservation is a word that's used a lot in physics. It means a lack of change of some quantity. There's four big ones that we'll study, or you may have already studied. There's the conservation of mass energy. You've, I'm sure, heard the conservation of mass and the conservation of energy. They're actually two sides of the same coin and get combined into one law. That was an Einstein thing. There's a conservation of linear momentum, conservation of angular momentum, and the big one for today is conservation of electric charge. So what conservation means is that in a system, so some slice of the universe you're choosing to look at, these quantities don't change unless your system interacts with something else, an outside force, some other charges, some gravity. If something is interacting with your system, these quantities could change. But inside a closed system with no outside interaction, these values do not change. And that's called conservation. So next we have to look at what exactly charge is. So some people have just the definition that charge is electricity, or the charges are positives and negatives. And those things are somewhat true in a less pure sense. Charge is actually the property of an object that allows it to interact with electric fields, which sounds kind of like mumbo jumbo. So to consider this, we're going to think about an analogous force, and that force is gravity. So the way that we interact with gravity, a gravitational field, for example, the gravitational field of the Earth, is that we have mass. We feel gravity because we have mass. Charge is very similar to that, except instead of feeling the force of gravity, charge is how something feels an electric force. So it feels an electric force in a field because it is charged. And if you watched the Richard Feynman video from yesterday, where the guy asks why magnets repel, and Feynman sits there and goes on and on and on about, a lady slipping on ice. But his point is that eventually there's got to be some fundamental thing that is understood and not questioned. And one of those things in physics is that charge is simply a property that interacts with electric fields. There's not really a why or a how beyond that. It's just simply something that is and that we've observed and we say is fundamental. So our discussion of electric charge today is going to be inside the framework of how it was discovered using the scientific method. So the scientific method looks like this. You observe something happen. Whatever happens is called a phenomenon, really regardless of how cool it is or not. But we call it a phenomenon. After you see something, a phenomenon, you try to explain it. So you come up with what you think is a reasonable explanation, and you call that your model. All of the parts of your explanation make up the parts of your model. After you've settled on an idea and you've formalized it, you've written it out, you've said, this is what I think happens, you work out the consequences of that model. So the consequences are basically the implications, the thing that the model says will happen if it's true. So you figure out what that is and see if it matches up with real life or if it matches up with experiments. If it does match, you say your model could be true. If it doesn't match, you go back to the drawing board and try to find a new model. Technically, we could never say a model is necessarily true because we don't have all the evidence in the universe. There's still things out there that we don't know. Things about dark matter, things about dark energy. So no one's model is ever proven true. It's just not yet proven wrong. But anyways, the first guy to use the scientific method to figure out about charge was Benjamin Franklin, back in the early 1700s. Pretty cool guy. He invented a wood stove. He became a postmaster general right after, he helped found America. But one of the best things he did was study electricity. And he started out with a phenomenon, or several phenomena, if we're going to use the plural. And the thing that he observed was that if you take glass rods and you rub them with fabric, like silk or wool, they start to repel against each other. And likewise, if you rub amber with silk or wool and you put two pieces next to each other, they start to repel as well. And this was while these objects were separated, which was a really foreign concept to anybody in that day and age, because a force acting over a distance was really weird. Most forces we knew about were contact forces. So Franklin came up with this model that objects rubbed with fabric became charged. And we're going to determine the same things that he did about charge based off of the following experiments. The first experiment we're going to look at is when you rub two of the same thing with wool or silk or some sort of fabric, what happens when you put them together. So if you rub two plastic rods, because we're going to use plastic instead of amber, we don't really deal with amber, it's not readily available, so we're going to use plastic, even though I know this is a slideshow. So if you take two plastic rods, you charge them up by rubbing them, they repel. The same thing happens with silk and glass. A glass rod that has been charged with silk repels another glass rod that's charged with silk. So what Franklin deduced here was that charges that were the same repelled. Now in a second experiment where you mix the materials, you take a charged plastic rod and a charged glass rod and you put them next to each other, there's attraction instead of repulsion. So what this tells us is that unlike things attract. And lastly, if you take two rods that haven't been charged at all, they don't attract or repel. They're neutral. So Franklin made his model based on these three experiments, And his model was that there were two types of what he called fluid, what we called charge. The two types are positive and negative. His model included the idea that like charges repel and unlike charges attract. This model still holds today and is compatible with all evidence we found. Now, to make our model a little bit more precise, a little bit more accurate, we can do some more experiments. The first experiment we're going to look at is a variation in the distance between the two rods. So if you charge these two rods the same way, they're going to have the same charge, which means they'll repel. But if you put them very close together, it repels more than if you put them further apart. So what that tells us is that the force between the two things is based on distance. As distance decreases, the force increases, and as the distance increases, the force decreases. It's an inverse relationship. Another experiment that is used to determine a further piece of our model is charging a plastic rod and then taking the wool you use to charge it and seeing how they interact. So if you take the plastic rod, you charge it, and you put the wool next to it, they attract. And what that tells us is that they must be opposites, okay? Because opposites attract. What we can take away from this is that when you charge something or give charge to one thing, it moves the object it took charge from in the opposite direction. So if you charge a plastic rod to be negative, then whatever you use to charge it is going to become positive. And this is because of that conservation of charge inside a system. So based off of all of these experiments, Benjamin Franklin and us, we came up with this charge model that you can use frictional forces by rubbing to add charge to an object or to remove it, that there are two kinds of charges, positives and negatives. Like charges repel, opposite charges attract. The force between two charges acts over a distance, so the two objects don't have to be in contact, and the amount of force varies based on how close or how far apart they are. We also know that neutral objects have both positives and negatives. That comes more from an atomic standpoint, and that charge is conserved in a closed system. So here we're actually going to draw some charge so we can get an idea of what it would look like and how to draw it if you're ever asked a question about it, because you will be. So we're going to draw a piece of wool. This is my terrible piece of wool, and a plastic rod. Okay? Wool and plastic rod. Now initially, they're neutral, and in our model, neutral things are just balanced between positives and negatives. So I'm going to make a balance between positive and negative in each of these two objects. So if I put 3 positives in the wool and 4 positives in the rod, I also have to go back and balance this out with negatives. So 3 negatives in the wool and 4 negatives in the rod. Now these numbers are arbitrary, chosen by me for no apparent reason other than that's what looked like would fit inside of my drawing. But that's fine. It just shows that they're neutral, things are balanced, because I've got the same number of positive and negative. Now, when we rub the wool or the silk on the rod, some charge is going to transfer from the silk to the rod or vice versa. Now, something to note is that charge always transfers negatives. So at an atomic level, what's happening is that there are atoms that have a positive nucleus because of protons and a negative electron cloud floating around them. Now, the electrons are mobile and they can float between atom to atom in a process called ionization. However, protons are stationary. So when we talk about charge transferring between objects, we mean that electrons are moving. So negatives are going to flow from one place to another. In this example, we're going to say negatives are going to flow from the wool to the plastic. So to draw that, I'll draw another set of things here. We've got a rod, And the wool, same ones, but after you rub it, the bottom's going to take the negatives of the wool. So it's going to have 1, 2, 3, 4, 5, 6, 7 negatives, and it's same for positives. And then the wool is just going to have positives. So now instead of being neutral, the wool has an overall positive charge and the rod has an overall negative charge. Now you can take it a step further and you can erase things that cancel out. So we could take a positive and a negative here, erase them, a positive and a negative, and another positive and a negative, until we have the total charge. So the top one, the wool would have a total charge of +3, and the bottom would have a charge of -3. Now something to note here that's, always going to happen in a closed system is that charge is conserved. So the top picture here shows them both neutral and the total charge is 0. So I'm going to write that as the sum of Q. Q is for charge equals 0. And for the bottom picture, if you do the same thing, a +3 and a -3, the sum of the charge equals 0. This will always be the case. In a closed system, whatever charge you started out with has to be the same charge you ended with because of those conservation laws. All right, next we got to talk about insulators and conductors. You probably already know what they are. Insulators are materials that don't really conduct electricity, is I'm sure what you've heard. And the reason that is because charges that are inside the material remain immobile. They don't move. And electricity is movement of the charge. Conductors, however, allow charge to move easily through them, and that's usually because they've got a lot of extra electrons that can scoot around because they're not held super tightly by the atoms. But what we need to focus on here, the biggest thing, is that charge spreads out uniformly on the conductor surface. Okay, and I'll draw a picture of that here in a minute. Charge spreads out uniformly on the conductor surface. So, if we have a conductor, we're just going to make it a sphere because spheres are nice and easy. And we give the sphere a net charge of -8. So say we touch it with something like a rod that's negatively charged. We give it -8 coulombs. That charge gets spread out along the surface of the sphere. It doesn't go in the middle. It gets spread out all around. And that's because charges that are the same repel. So they're trying to get as far away from each other as they can by spreading out on the surface uniformly. And this is going to be really important later when we're working on figuring out some charge distributions and the way certain things will behave. So you have to know that conductors have charge that is spread out uniformly, and that thing or that state is called electrostatic equilibrium. We've got a couple of experiments we're going to look at here real quick. They're pretty obvious. But this first one is taking a charged plastic rod, so something we charged with wool. Just for argument's sake, we'll make it negative. Have a negatively charged plastic rod, and we touch it to metal, which is a conductor. That negative charge is going to flow from the plastic into the metal. And when it does so, it's going to spread out all around the surface of the metal. So really, all that this adds to our model is that something that's charged will transfer its charge to a conductor whenever they touch. But this only happens when contact happens. So if you just held the plastic close to the metal, the charge wouldn't move. It has to be touching. However, if you take a charged plastic rod and you touch it to some metal that's connected to another plastic rod, which is connected to another metal sphere, it's a little bit different. So we're going to start off with the negative plastic rod here. And when it touches the metal, the charge spreads out uniformly around the metal. So the rod's going to be neutral now, and the metal is going to be charged. However, this middle rod that's plastic is an insulator, and insulators aren't going to conduct the charge. So the charge is not going to go from this metal ball to this one over here. Okay, it's going to stay in the first one. It does not move through the plastic rod. So in the end, the first metal ball, the one that was touched, will be charged, and the second one will remain the same as its first state, which was neutral. Now, if instead of connecting them with a plastic rod, we used a metal rod, here's what would happen. The plastic would be charged negatively. We'll say it's with 4 negatives. When the plastic touches the metal, it's going to transfer over to the metal. So this first metal ball will have all of the charge. However, since they're connected by a long metal rod, the charge is going to spread out evenly over this whole system here, okay? Over all the conductors. So 2 of the negatives are going to move over to this metal ball, and 2 are going to stay on the first one so that it is evenly split. We're going to ignore the metal rod right now. We're going to say it's negligible. So if they are connected by an insulator, the charges can't move, but if they're connected by a conductor, it spreads out uniformly. So to summarize that and add on to our charge model, we're going to say that all materials are either conductors or insulators, and charge is only transferred by contact. And to summarize the behavior of those conductors, the charge is going to spread out over the whole surface because like charges are trying to repel. And when a conductor is charged, the charges move really quickly. It happens almost instantaneously, and it reaches electrostatic equilibrium. So to model this again, just make sure we got it. We're going to look at 2 spheres connected by a metal rod and a second rod that has an initial charge of 6 positives. Now, when that contact is made with a conductor, the charges are going to move from the rod to the conductor. But since everything here is a conductor and it's all connected, it's going to spread out evenly over the whole surface. So the 6 positives from the rod are going to move into the spheres, and we'll have 3 positive charges per sphere. And now we're going to get into a tricky little thing called polarization. So polarization occurs on neutral objects. And we're going to start with a neutral object here, okay? Now, neutral here does not mean it has 0 charge anywhere in the substance. It means that it has 0 net charge, because we know that everything's made up of atoms, and atoms have protons and electrons. Protons are positively charged, electrons are negatively charged. So it has both inside. It just means it's balanced. So this neutral sphere is going to have a balance of positive and negative. I'm going to do 4 of each. 4 positives, 4 negatives. So its net charge, its total charge, balances out to be 0. But now what we're going to do is we're going to bring a charged rod near it. Not touching, just near. Okay? We're going to make it positively charged. Now those positive charges are going to interact with the positives and the negatives that are inside of the sphere. So the positive rod is going to pull on the negative electrons, and it's going to push against the positive protons, which is going to change our charge distribution to look like this. Something to note here is that the negative electrons moved, however the positive protons did not. It's just that now this side over here has less electrons, so it's more of a net positive. Now the overall charge of the sphere is still neutral. However, the force between these positives and these negatives is acting over a really short distance. And the force between the positives is acting over a really long distance. And part of our charge model states that forces are greater at a closer distance than at a farther distance. So what this means for our model is that overall, the force experienced by the sphere is really big towards the rod and pretty small away from the rod. So as a net force on the sphere, it's going to be pulled towards the rod. And this effect is called polarization. Polar means there's two sides, a positive and negative. So the sphere gets polarized. One side becomes negative, one side becomes positive. And it's going to be pulled towards the rod. This effect is responsible for a whole lot of things in chemistry and can be applied to atoms and molecules, which end up with sometimes a more positive or negative side. All right, so to do a quick little check, answer a couple of questions, we're going to look at this one. A rod attracts a positively charged hanging ball. The rod is positive, negative, neutral, or a combination. So the obvious answer here is that the rod is negative because positives and negatives attract. And that is true. Negative is correct, or negative is part of the answer. However, we just saw that a neutral object can be polarized to be attracted by a charged object. So a positive sphere here would pull the negatives to one end and leave positives on the other, so that the attraction is greater on this side than the repulsion on this side, and the net force is in the direction of the charged sphere. So due to polarization, this rod could either be negative or neutral, and that answer choice is answer choice E, the correct one. All right, next one. Metal spheres 1 and 2 are touching. Both are initially neutral. And then we've got this process we're going to go through. And I'm going to draw it as we go. So both spheres are neutral. We're going to leave them as they are drawn. The charged rod is brought near. So when the charged rod is brought near due to polarization, some negatives are going to be pulled to this end. And that's going to leave the other side more positive. Now, because the two spheres are touching right there, we consider them as one system. So we'll pull negatives and put them in one sphere, and positives will go on the other sphere because they're connected. Then the charged rod is removed. Now, if the charged rod is removed, the conductors are going to resituate themselves back into electrostatic equilibrium where everything is balanced. So the negatives are going to go back to where they came from, and everything's going to turn out neutral again. So we'll have the same amount of positives and negatives on each side. Everything will be back to the way it was. Let's see, let's get it back there. All right, so when we separate the spheres again, which is letter C there, they're going to have net charges of 0, which is answer choice E. However, if we change that procedure a little bit and we bring the rod near, which separates the charges again, we'll have negative on this side, positive on the other. And we leave the rod there, so the charges are staying the way they are, and we separate them, okay? So there's no more contact, no more charges can flow. The net charge on sphere 1 is going to be negative, and the net charge on sphere 2 is going to be positive, which is answer choice C. All right, a couple more before we move on to the atomic model. So this one has 3 spheres. Their charges are shown. That little NC is nanocoulombs. So we start off with spheres P and Q, and we're going to touch them together. And we're going to draw this real quick with all of the little charges. So if you've got P and we've got Q, P has 4 positives, 2, 3, 4. Q has 2 negatives. And we touch them together, connect them. Okay. The charges are going to spread out to be even. So we're going to take one of the negatives from this sphere and put it over here. And we'll take 2 of the positives from this one and move them over so that everything is balanced. I have 2 positives on each side and 1 negative on each side. Now each sphere has a charge of positive 1 overall. So P has positive 1 and Q has positive 1. And then R is still sitting over here with negative 1. All right, and then we're going to touch spheres Q and R together after that. So now we've got Q and R. These positives are going to split up. We're going to take one of these positives, scoot it over here, erase it on this side. And now each of these has a net charge of 0. Okay? So something to note here is that in our system, the system of these 3 spheres, the charge at the end, the total charge, if you add all 3 up, is positive 1. Now let's go check. In the beginning, with these charges, our total charge is 4 minus 2 minus 1 equals positive 1. So our charge was conserved. We started with the same amount that we ended with. And our answer over here, the charge on sphere R at the end is going to be 0, which is the correct answer. All right, moving on to atoms and molecules. We're just going to talk about it very briefly. We've kind of already hit on it. But the model of an atom is that there is a positively charged nucleus. So positives in the middle. And floating around the outside on orbits are electrons. I know this is not how orbits actually look. I do understand electron levels, but I'm not going to worry about drawing them right now. So the model of the atom is that there's positive in the middle, electrons on the outside. The protons are what determines the element. They don't really move. They don't really budge. They always stay in the middle. But these electrons on the edge can be stripped off by other atoms, and that's a chemical thing called ionization. So we're not going to go too much into it at all, but electrons are the things that move out of the atom. They are the thing that's going to transfer the charge. Anytime we're moving charge in a system, it's going to be the electrons that move that. Now, all electrons have the same charge. That charge is this number right here, 1.602 times 10 to the negative 19th coulombs. And that is negative for electrons. It's positive for protons. Protons and electrons are exactly evenly balanced. Now, this is also called E. E is the fundamental charge. It's E for electron. And it's that number right there, always a constant. So atomic theory says that there are equal numbers of protons and electrons in an atom. So they're always neutral, which is why most matter is neutral, unless they're ionized, which happens in chemistry. And that's the process of an atom gaining or losing electrons. If it gains electrons, it becomes more negative. If it loses electrons, it becomes more positive. And then in insulators, the electrons are super tightly bound to the nucleus, so they aren't readily gained or lost, and it's really hard to transfer charge through them. However, conductors have lots of free electrons that are easily given away, and that happens with most metals. And one last little bit that we got to do before this lecture is finally over, is one last calculation, or I guess really one first calculation. And that is using this number to figure out a number of protons and electrons. So we're going to read the question. It says a housefly walking across a surface may develop a significant electric charge because its little feet are rubbing on whatever surface it's walking. Suppose a fly picks up a charge of 5.2 times 10 to the negative 11th coulombs. Did it gain protons or lose electrons, and how many? So the first question, gaining protons or losing electrons. Gaining protons is not a thing that happens. The protons are not what transfers charge. It is the electrons because they're on the outside of the atom. So we're going to choose here losing electrons. That's the answer. And now we got to figure out how many. So to figure out how many, we got to use a wee bit of math, and we're going to do a proportion. So we know that the fly picked up this much charge, 5.2 times 10 to the negative 11th coulombs. And all that's left to do is figure out exactly how many electrons that is. So we say 1 electron is 1.60 times 10 to the negative 19th coulombs. And that's equal to some number of electrons out of this charge that we came up with here. This is just a proportion like in math. Okay, so 1 electron, sorry, that looks like a negative. 1 electron, make it a star, has that much. How many electrons has this much? So to solve for x, you multiply both sides times 5.2 times 10 to the negative 11th. And you just type that into a calculator and compute it out. So x equals 5.2 times 10 to the negative 11th over 1.6 times 10 to the negative 19th coulombs. So whatever that is going to be the answer to this question. So that's it for today on electric charge and its behavior. Stay tuned for another day on Coulomb's law.